So assignment, momentum and collision. I'll discuss the doubts related to this assignment. The first one is question 1, the doubt. The diagram shows momenta P and Q of two bodies about to collide. So two objects are colliding. When the bodies collide, they merge and move as a single body. Which of the following diagram shows the resultant? So how we will work out the resultant? So what we have to do, we have to add, because this is like a vector addition. So if we add, like we have momentum P is there. Then we have momentum Q. So what about the resultant here? How to work out the resultant? Resultant is from tail of the first to the head of the last. That will be the resultant momentum. So which one it match with when you check in terms, because it should be accurate according to the directions as well. So Q is pointing in this manner. So P and Q, so if you want to work out the resultant, it is from the tail of the first to the head of the last. That will be the resultant. So the resultant, it matches with option C. So C will be the right answer for this one. Next is question 7. So in question 7, the particle Z is having a kinetic energy E and the momentum P. And the second particle X, which has a twice mass and half of the momentum, the kinetic energy of X will be. So what is the relation? The kinetic energy, or EK, is equals to half mv square. The formula which relate the momentum and the kinetic energy, if we multiply this and divide this equation by m, so it means EK is equals to half m square v square divided by m, because we divided by divide and multiplied by m. Then m square v square is momentum, because the momentum is a product of mass and velocity. So mv is a momentum and m square v square is a momentum square. So we can say EK is equals to p square over 2m. So according to this formula, the kinetic energy is proportional to momentum square, and kinetic energy 2 is constant, and the kinetic energy, or K, is inversely proportional to mass of an object. So what happened? The second particle has a twice the mass and half momentum. So if the mass is twice, if one is increased, what will happen? The kinetic energy will decrease by 2. And what about the relation between momentum and kinetic energy? They are proportional with square, means if we double the kinetic energy, if we double the momentum, kinetic energy will be 4 times. Same way, if we halve the momentum, kinetic energy will vary with the square of that number. So the square of 2 is 4. So it will divide by 4. So what is the overall change in the kinetic energy, K? What is the overall change? That due to change in the momentum, it decreases by 4. And due to the change in mass, it decreases by 2. So what is the overall change? It will be AK by 8. That's why option C is the right answer. So the relation between momentum and the kinetic energy, that kinetic energy is proportional to momentum square, and kinetic energy is inversely proportional to mass of the particle when we have this formula. This is the formula which relate kinetic energy, momentum, and mass of the particle. Is it clear, this one? The next question is 12. So again, this was related to the formula which relate the kinetic energy, momentum, and mass of the particle. A proton accelerates in electric field and it gains the kinetic energy and giving it a change in the momentum delta p. Alpha particle. So when we compare the mass of the proton and mass of the alpha particle, because alpha particle consists of two protons and two neutrons. So its mass is 4 times. If the mass of proton is m, the mass of alpha particle will be 4m. The magnitude of change in momentum of the alpha particle is given by. So how we can work out, again the same formula, that kinetic energy is equals to p square over 2m, or under root and they already mentioned it gain the same kinetic energy. The kinetic energy is same for alpha particle, and you can compare with the mass directly, or you can also use the equation like if I say the formula is Ek is equals to p square over 2m. So for proton, the kinetic energy of proton example Ek, the momentum of proton is example p is there and divided by mass 2m. But for alpha particle, the mass, the kinetic energy is Ek, momentum is p dash square, like momentum of the alpha particle, divided by mass is 2. 2 is the for formula, and the mass then divided by 2m, where m is equals to 4 times, so it will be 4m. Now, when we simplify this, because they both have the same kinetic energy, so kinetic energy of the proton is same as the kinetic energy of alpha particle. Here it will be 4m. So m will cancel with m. This 2 will cancel with 2. So this 4 is divided. Other side will be multiplied. So 4 times the momentum of proton is equals to the momentum of alpha particle. So what about the momentum of alpha particle? If we take a root, so if we take a root, 4p square is equals to under root p. So 4p square is equals to 2p and p dash. So it means the momentum of the alpha particle is twice the momentum of the proton. That's why option B will be the right answer. This is one way. The second way, you can directly use this formula, like kinetic energy is p square over 2m. So kinetic energy into 2m in a root is equals to p square. They mentioned kinetic energy is not changing, same. So what is the relation between the momentum and the mass? So the variation here, that momentum is proportional to under root of the mass. And as we know, the mass become 4 times, so it increased by 4. So what will happen to momentum? Momentum will increase by root of that number. So what is under root 2? Under root 4, so that under root 4 is equals to 2. So this will increase by factor 2. So either you can use this relation, or you can compare that the kinetic energy of the proton will be equal to kinetic energy of alpha particle. Kinetic energy of proton is p square over 2m, where kinetic energy of the alpha particle is like this momentum is p dash square over 2 into 4m. So when you simplify, you will get that the momentum of the proton, the momentum of the alpha particle is twice the momentum of proton. That's why option B is the right one. In question 13, a sphere of mass m1 moving with velocity u1, elastic collision is there with a stationary sphere of mass m2, and they move with angle theta and phi. Which of the following applies to direction of u1? u1 is x direction. So we have to divide into components. So this is making angle theta. So the one, because the momentum is m into u. So the component of the momentum which is with an angle, that will be m2 u2 cos theta. And against the angle, this will be the horizontal. And against the angle will be m2 u2 sine theta. Same thing with an angle for m1 v1. So this will be m1 v1 cos phi. And against the angle will be m1 v1 sine phi. So we need in x direction. So the total momentum before collision. So this will be m1 u1. This is 0. The total momentum after collision. So it will be m, because this is m1 v1 cos phi plus m2 v2 cos theta. So m1 v1 cos phi plus m2 v2 cos theta. So it matches with option A, because we need in a direction of u1. U1 is in x direction, so we just take the component in x direction. We don't have to bother about y direction. Use the same figure. Which of the following equation applies if the collision is elastic? So for elastic collision, the total momentum before is equals to total momentum. The total kinetic energy before is equals to total kinetic energy after. And kinetic energy is a scalar quantity. So it does not, we don't have to consider a direction. We just need the mass and speed. So what is the kinetic energy before? It will be half m1 u1 square. This will be 0 because it is stationary. What about the kinetic energy after? It will be half m1 v1 square plus half m2 v2 square. Because when we are talking about kinetic energy, it's a scalar quantity. So we just need the mass and the velocity. We don't have to bother about which direction the particle recoil or move or deviate after the collision. So this one, it match with option C. So C will be the right answer. So when we talk about kinetic energy, we don't have to consider the angles. In question 15, which of the following is a possible unit for rate of change in momentum? Rate of change in momentum is also refers to the force, because F is equals to ma. And acceleration is change in the velocity, so it is v minus u over t. So F is equals to mv minus mu over t. That mv minus mu over t, that is the rate of change in momentum. So that is equals to force. And what is the unit of the force? The unit of the force is Newton, but the base unit, Newton itself is kilogram meter per second square. So this will go up. So it will be kilogram meter second minus 2. That's why C will be the right answer for this. So rate of change in momentum is also a force. So they're asking the unit, the base unit of the force here. Next is question 16 part B. So initially the spring was fully compressed. As the toy was released, the head accelerates upward on its own until the spring is uncompressed. The head then pulls the base upward and then move together with the same speed. The student used the elastic potential energy stored in the spring to determine the maximum speed of the head. The student used the gravitational potential energy gained by the whole toy to determine the initial upward speed. Determine whether the toy obeys the law of conservation of momentum. The speed calculated this way. The mass of the head is 6.4 grams. The mass of the whole toy is 7.2. And the maximum height which is lifted is 1.5. So what we will consider the total momentum before, when the head was moving only, and the toy, the total complete toy is moving, the total momentum should be conserved. Like the total momentum before collision should be equal to total momentum after. or total momentum before this spring move, like the whole toy move, or first its head was accelerating, so that is the momentum of the head will be equal to the total momentum of the toy as well. So first, using the potential energy mgh, we'll find the speed at which the head is moving. And from speed of the head, mass of the head multiplied by velocity of head, will get the initial momentum. And then we will work out the speed of the whole toy. And after working out the speed of the whole toy multiplied by mass of whole toy, we'll get the final momentum, and the initial and the final momentum must be equal, because the total momentum before the collision should be equal to total momentum after the collision. So the first part, the student used the elastic potential energy stored in the spring to determine the maximum speed of the head, and the gravitational potential energy gained by the whole toy to determine the initial speed. So using the elastic strain energy, we'll find the speed of the head, and using the potential energy, we'll find the speed of the toy, and using the speed of the head into mass of the head, we'll get the initial momentum, and using the speed of the toy multiplied by the mass of the whole toy, we'll get the final momentum. And if it is momentum is because if both momentums are same, it means the momentum is conserved. So how to work out the speed at which the head is, because it is related to previous part as well, as I mentioned, that the energy stored is 0.1. So that will be the kinetic energy. So first we'll determine the speed of the head. So for head, so first we'll determine the speed of the head. So how to work out the speed of the head? The elastic strain energy is equals to kinetic energy. So elastic strain energy and kinetic energies will be equal. Kinetic energy is equals to half mv square, and elastic strain energy, that is equals to 0.1 joule, or the answer which we get in the previous one. So the mass of the head is there, which is in gram. Here it's given. We have to convert into kilogram, like it will be 6.4 into 10 to the power minus 3, or it will be 0.0064. So it will be half into the mass 0.0064 into the speed we don't know, and the energy was 0.1. Using this, after taking a root, we'll get the speed, which is 6.1 meter per second. Now to get the momentum of the head, the product of mass and velocity. So mass is 0.0064 and the velocity is 6.1. So when we multiply them, we get 0.039 kilogram meter per second. That's the momentum of the head. Now the momentum of the whole toy, as this toy is, the whole toy is lifted to a height of 1.5 meter. So means that whole toy, for the whole toy, and we assume there is no loss of energy, so the kinetic energy will be equal to potential energy. Kinetic energy again, half mv square, and the potential energy is mgh. So m will cancel with m. So v square is equals to gh, or we can substitute the mass of the whole toy here, as we already have the mass. Then what about the mass of the whole toy? That is the sum of the head plus the base. But they already mentioned that is 7.2. So it will be half 7.2, 0.072, 0072 into v squared into The mass 0.0072 into gravity 9.81 into height. It moves to a height of 1.5. When we simplify, we'll get the speed of the toy, which is 5.42 meter per second. Now to get the momentum of the toy, so which is a product of mass and velocity, so the whole toy is 0.0072 multiplied by 5.42, which is 0.039 approximately. So it is kilogram meter per second. So you can see the total momentum when the head was moving is same as the total momentum when the whole toy is moving up. So it means the momentum is conserved. Is it clear, this question? Then next is question 20B. In question 20, a student read the following extract from a book. In elastic collision between the objects, equal masses where one initially stationary and other move off at 90 to each other after collision. Student investigated this using the collision of two identical balls, each of mass 66 gram. The diagrams illustrate the collision between the balls before the collision. One is stationary and then after. In one experiment, the initial velocity was 0.72 and the angle was 29. For a collision, it can be shown that if the balls are separated at an angle of 90, then V1, phi, use these values satisfy the conservation of momentum in initial direction of ball 1. Initial direction of ball 1 means x direction. We have to take the conservation of momentum in x direction. That is m1 u1 plus m2 u2. Like the mass of the ball into its velocity. The mass of the ball initial momentum is the mass is equals to 0.066 because 66 gram is there. And the speed at which this was moving, that is 0.72. So this will give us the initial speed. U1 is how much? U1 is 0.72. So U1 is 0.72. When we multiply, we'll get the initial momentum, which is 0.048 kilogram meter per second. Now we need the momentum here. This masses are same. So this will be the horizontal. We just need the horizontal component. We'll add for both of them. So the horizontal component, this horizontal component will be because masses are same, so it will be m1 v1 cos theta and m2 v2 cos phi. So m1 0.066 multiplied by v1 that is given in the question. V1 is 0.63 and the other one is 0.35. 0.63 and cos the angle which it was making, that is 29, plus the second one 0.066 into the mass, which is The mass is there into velocity 0.35 into cos 61. The initial, the angle of this sphere. When we sum them, this will give us about 0.048. So it means kilogram meter per second. It means the momentum is conserved in x direction. In part, show that these values satisfy the condition of elastic collision. So we have to calculate the kinetic energy before and after. We don't have to bother about the angle. The next one, the photograph shows the student actual result of this experiment. The position of the colliding balls are at successive time interval have been overlaid on a single image. So you can see the motion of the ball 1 and 2. We state additional information that student need in order to determine the speed of the ball. So how the student can determine the speed of the ball? Because speed is distance divided by time. So what we need, if we measure, like we should first know the scale of this image. Like 1 centimeter, example, if this was, this line is representing 1 centimeter. So it is actually equal to how many meters? So first thing we should know scale of this image. And the second thing we should know the time, because using the scale will determine the distance, and time and distance divided by time will get the speed. So we need the scale of this image and the time interval to work out the speed. The student look at the photograph and notice that the angle between the path of two balls after the collision was not 90. He modeled the collision on the computer. He used same initial velocity for ball 1 and same angle theta. The computer calculated the total kinetic energy after collision for range of phi. Measure phi from the photograph and use the graph to suggest why the angle between the path is not 90. So we have to measure a phi from the photograph. So how to work out the phi from photograph? As you can see, phi is the angle of the second ball with horizontal from the initial direction. So what we have to do, we have to draw a horizontal line. Like this is basically the line in which the ball 1 is moving. And we have to measure this phi. So this angle will be the phi. And the sum of phi and theta should be 90. So if we take or measure from the figure, say the phi is coming out 50, example. So if the phi is 50, what we will do? We'll work out the kinetic energy, the total energy after the collision. And this total energy after the collision, in the example, it is 0.014. And but the total energy before the collision is 0.017, as it is done in the previous part. This part, when you will solve, you will work out the total energy before and after. So that is about 0.017. So working out the phi, after working out the phi from the figure, you will draw a line from that angle of phi from your figure. Then work out the kinetic energy, the total energy after collision, and compare this total energy with the total initial energy. The total initial energy is half mv square, which is the mass of the ball 0.066 half, and the speed is, so it will be half into 0.066 into 0.72 square. So when you solve, it is 0.0171 joule. So means this is 0.017 joule and this is about 0.015. So what it shows the kinetic energy before and after are not equal. So before and after the kinetic energies are not equal. What this give an evidence? This give an evidence that this momentum, this collision is not an elastic collision, it is inelastic collision. that how we work out that if the total energy after the collision is coming out 0.017, it means that this momentum will be the kinetic energy is conserved. So collision will be a elastic collision. Then 22 part B. The student vary the angle at which he hold the hair dryer. The graph for force acting on the electronic balance against sine theta is plotted. The student assumed that the air behaves as in part A. Show that in case the gradient of the graph is equals to 2v square A into density. So how we can show the gradient is about this value. So gradient is the quantity on y-axis divided by quantity on x-axis. That's the gradient of the graph is the quantity on y-axis divided by quantity on x-axis. That's the gradient. So in this case, the quantity on y-axis is force and quantity on x-axis is sine theta. So it is equals to, the gradient will be equal to F divided by sine theta. Then what about F, the force? As in the previous part, you can see here, F is equals to 2mv sine theta over t. So F divided by sine theta is equals to 2mv over t. So we know the gradient is equals to F divided by sine theta according to the graph. And F, according to this formula, F over sine theta is equals to 2 mv over t, where m is a mass, v is a velocity, and t is a time. And then in the question, they mention the mass of air striking the electronic balance per unit time is given by VA rho. So mass per unit time, this mass per unit time, m by t, is equals to V, the speed, A, and rho, the density, and this is their mass per unit time, and then V is there, the speed. When we multiply, so this will be equal to 2 V square A over A into rho. So it shows that the gradient is equals to 2 V square A over A into rho. Is it clear? So first we work out the gradient will be equal to F by sine theta. Then F by sine theta according to formula is 2 mv over t. And according to the average mass of air striking per unit time means m by t is equals to the speed multiplied by area multiplied by density. And then we substitute, we'll get 2 v square A into rho. Then calculate the speed of air. So how to work out the speed? You already worked out the formula. You already work out the formula 2v square A rho. The gradient, so gradient is equals to 2v square A and rho. Now what we will do, we will use our graph to work out the gradient. And we have the area, we have density, so we can work out the speed. So this graph is there. So you have to draw a best width straight line first. After drawing the best width straight line, find the gradient of this, which will be y2 minus y1 over x2 minus x1. And the gradient is equals to 2v square A and rho. So you will get the gradient from graph, area is given, density is given, so you can work out the speed at which this air will come out from the hairdryer. Suggest why the speed calculated in V2 might be incorrect. What might be a reason? Because the hair drive, its temperature is changing continuously, so the density of the air changes. And another reason, all the particles are not hitting with the same angle, that may also affect the speed of the air drive, the particles. Then question 25, state the conservation of momentum, principle of conservation of momentum. The total momentum before collision is equal to total momentum after the collision. And in the absence of any external forces. Then there's a head-on collision between beryllium and neutron. Calculate the velocity of beryllium atom, indicate the direction by adding an arrow. So example, if we consider it move towards right, and our final answer is negative, it means it move in opposite direction. Or example, if we consider it move towards left, and our final answer is positive, it means our direction which we assume or consider is correct. So we just need the velocity here. So the total momentum before collision is equal to total momentum after. So initial momentum of a neutron 1.67 into 10 to the power minus 27 into speed 3250. But because the other particle is moving in opposite direction, so we have to take, like this is, if this is a positive momentum, this will be negative, so minus 1.5 into 10 to the power minus 26 into 175, that is the total initial momentum. And the final momentum, as it gain, so the mass changes to 1.67 into 10 to the power minus 26, and the speed example is v. So we just simplify and get the value for v. And the last part, using a suitable calculation, determine the whether collision is elastic or inelastic. So when we are talking about elastic or inelastic, we don't have to bother about the direction. We'll just use half mv square for this one, half mv square for this one, even it is head-on collision. We don't bother about the direction, and half mv square for this one. And this is a total kinetic energy before the collision, and this is the total kinetic energy after. So if the two energies are same, the collision will be elastic. If two energies are not same, it means the collision will be inelastic. Likely, because head-on collision likely leads to inelastic collision. So likely it will be inelastic, like the sum will not be equal. So these are the doubts related to assignment, momentum, and collision.